So here is what we stopped last time in this example, but we didn't finish to the end. So in this example, we have the concrete strength was given to us as 4,000 psi. Yield strength is given the standard for the steel, 60,000 psi. And they say here, neglect the hanger bars, which means the compression reinforcement on the top. Provide that we have here positive moment. Therefore, the 3 number 8 is given the tension sign. And the question here, it says, determine the nominal moment strength, which is Mn, and the design moment strength, Pman. Now, for the tensor reinforcement here, I should be able to find out A sub S, which is the total cross-section areas of all these 3 bars, the 3 number 8. This is now is going to be perpendicular to the screen, and this is what we are going to be using in tension. If one rebar is going to have a cross-section area of 0.79 square inches, the question is, where did they get this from?
Is that the nominal area for number 8?
Yes, this is correct. Just bringing some people in. Yes. This is the first slide set. And we have here some information about the rebars. For number 8, nominal diameter is going to be 1 square inch. Excuse me, 1 inch for the diameter. And for the nominal area is going to be 0.79 square inches. Don't try to say pi times 1 squared divided by 4 and try to find this out, this cross-section area. Please don't do it this way. You just read it off this table, because the other way it's going to give you here different answer. So we're going to be looking here at AS, and AS is going to be equal to 3 times 0.79 that we just read off the table. It's going to be 2.37 square inches. And for the depth, I understand that this 1.5 inch is going to be the clear cover. If you like, I can just draw this quick line here to show you that this goes to the bottom of this rebar. It's going to be going to here. We're right here at the bottom of the tie. Now, the tie itself, it has a diameter of 0.5 inch because it says here number 4 times. This 14 inch, the spacing of the tie perpendicular to the screen is not critical to me in my analysis at this point. Now, this bar diameter is an inch. So what I'd like to do is to find out the depth to the center of this rebar. So what I have here, I have 0.5 inch for the tie diameter, another 0.5 inch for the bar radius, for this bar radius, the main reinforcing. So I have here 1 inch. So you add this 1 inch to 1.5, you're going to have 2.5 inches from the bottom of the beam to the center of the rebar. That's why you see here this 2.5 inch. And for that, the depth is going to be equal to 16 minus 2.5 inch, you end up with 13.5, like what we are looking here at, 13.5 inches. So in this case, this piece of formation, this is what we call here the clear cover. In some cases, D can be just given to you directly. You don't need to care about the bar diameter of the tie and the bar diameter for the main reinforcement. You don't have to do all of these deductions in this analysis. You can just be taking this depth right away. Now, if you said the tension is going to be equal to the compression, and the tension force is going to be equal to AS times Fy, we're going to set it equals to 0.85 F prime C, which is the block force, is going to be 0.5 F prime C, times the width B times the depth A. So if you take this multiplied by A, is going to be equal to AS times Fy. Now you set them equal to each other. You have AS, you have Fy, you have the width B, you have F prime C, that's 4,000, and with that you solve for A. A turned to be 4.18 inches from here to there. Now, if you like to get to C, what you need to do is to divide this A divided by beta 1. And beta 1 is going to be 0.85. Where do we have this? I'm going to say we have it from this slide, if you like. I'm going to just go back a few slides to remind you of this beta 1 determination. When the concrete strength is 4,000 or less, your beta 1 is equal to 0.85. For each additional 1,000 psi increase in the concrete strength above 4,000, you're going to be losing here 0.05 of this value. Once you hit 8,000, you're going to have a flat value of 0.65 for the beta 1. So what I said, okay, let me use here 0.85. If I take here A is going to be equal to beta 1 times C, take this A divide, which is 4.18 divided by 0.85, you'll get to 4.92 inch for the depth of the neutral axis. Now, what's the next step after you have this A? I guess someone's going to say, now I have the distance from the tension to compression. And this distance is going to be the distance from this point to that point. And how do you do this distance here? You say it's going to be equal to D the 13.5 minus A over 2, 4.18 divided by 2. This is simple, and now we have this distance. If you like, you call it Z, you can call it Y sub CT. Some people would call it like this. You're going to call it here Y CT, Y sub CT. If I may add this here, maybe just here, it's going to be equal to Y sub CT. You can use it this way if you want to. This is going to be okay. Or you can call it Z if you want to, like in the previous symbol we have used. Now you should be able to solve for the moment, but you have an assumption that you started with. You say that the tension equals to S times Fy. So you have an assumption here that the steel is giving the yielding region, like in the yield plateau. But you cannot confirm this. You don't know if this is true or not. Here's the stress-strain relationship. And you just assume here, in simple words, you have assumed, let me do this to be able to put some notes. I don't know what's wrong with this. So you simply assumed that the strain in the steel is given in this region. And the stress in the steel is going to be equal to F sub Y. But he did not confirm this yet. So what we need to do here, we need to confirm the strain in the steel. Now to confirm the strain in the steel, I have the concrete strain to be at 0.03, which means at the capacity point, concrete strain. I have the depth C, I have the depth D. I should be able to find out the strain in the steel. I can say, for example, that 0.03, which is a strain in the concrete, divided by 4.92 for one triangle is going to be equal to the strain in the steel divided by 13.5 minus 492, which is this distance from here to there. So this distance from here, neutral axis, to the bottom at the steel is going to be equal to 13.5 minus 492. So again, I'm going to say the strain in the steel divided by this distance is going to be equal to 0.03 divided by 4.92. And with that, I should be able to solve for the steel strain. It's exactly what we have here. Here is the strain in the steel. And it turned to be 0.005. The question is, how much is the strain here? The yield strain that you're talking about. How can I calculate that? I understand that ES equals F sub Y divided by epsilon sub Y. It's going to be equal to the stress divided by the strain. Looking for the strain at yield, what you need to do, take 29,000, which is E sub S, divided by 60. This is exactly what I have done here. I mean, just have said it, that was the inverse of it. It should be the 60 divided by, because this ES is going to be equal to Y component divided by the X component. So ES equals Fy divided by epsilon Y. So in a case like this, looking for the strain is going to be equal to F sub Y divided by ES. The 60 divided by the 29,000. With that, I have the 0.0021. Now, the strain I just determined here from this analysis, as we said before, it's going to be 0.005, larger than epsilon sub y. Therefore, my assumption that the stress in the steel is going to be equal to 60 is correct. All right. Now, once I have the strain, I should be able to solve for the phi factor. Here is the strain direction increase. The strain is going to be a little bit over 0.005. So my strain in the steel is going to be in this side. I'm going to go here with a vertical line. It's going to hit this solid line. Therefore, my phi equals to 0.9. Great. Now I have the phi factor. I have the strain in the steel. And I have all of these factors, like the compression force or tension force, as 142.2. I have the distance from the compression force to the tension force that we were just talking about. So what I need to do is to find out Mn. What is Mn? Mn is going to be equal to the tension or compression. And for here, I just pick the tension force, the 142.2, times d minus a over 2. Now again, what is d minus a over 2? It's going to be this distance from here, compression force, to the tension force. Why this is d minus a over 2? Here is d, total distance, subtracting 1/2 of a. Here is d minus a over 2. With that, I have the moment as in kip inch. I'd like to see usually the moment in concrete design is going to be in kip foot. So to convert from kip inch to kip foot, I'm going to divide it by 12. Any questions? No questions at all? Everything's good? All right. How can I get here to phi Mn? Just take Mn multiplied by the phi factor. So the 135.2 kip foot multiplied by 0.9, because I cannot really load this beam to that moment. So I'm going to reduce the moment as a strength to be 121.7 kip foot. And with that, I'm done with this example. Do you guys have any questions on the use of this table or chart? You're good? All right. Let's try this out. Now I want your help with me. I need it. I see here that on the x-axis, I have two parameters. The first one is going to be the strain in the steel. The second one is going to be C over D. So I decided here, I said, well, I'm done with the problem. But why don't I go back and try this C over D? I'd like to figure it out. I mean, how it is used. So I'm going to go back here and ask you simply. Now you have C and you have D. Can someone help me here and tell me how much is this C over D, this ratio? All right, Alfred, why don't you tell us this? How much?
0.36.
Point what? 36?
Yes.
Okay, Alfred, is this correct or is a little bit off? Alfred? Are you there, Alfred?
It's a little bit off.
Little bit off. So what is the exact ratio? Take 492 divided by 13.5.
Say that you went to the bathroom.
0.36.
Okay, you say 0.36.
It should be more.
Is it more or less?
No, the phi factor 0.9, so I think it should be 0.36.
So I'm gonna say 492 divided by 13.5. It's 0.364, right?
Yeah.
Okay, so I say, okay, let me use it here. I'm looking at this direction. This is here 0.375, right? It's gonna be right here. This here is gonna be 0.6. So what is the 3.36? It's gonna be in this side to the right, or it's gonna be to the left of this value? Direction
on the right side.
is giving the right. It is the same as this red line. So it is correct. I can either use this strain in the steel or use the C over D ratio. Both of them get me to the right place. But the good thing about using the strain in the steel, I was able to confirm it quickly to confirm my assumption that the strain in the steel is going to be larger than the yield strain. So if you are good with design, you can just say C over D is going to be equal to this. And since this value here is going to happen at the strain of 0.05, 0.005, therefore the strain here is more than 0.005, and we have a strain in the steel higher than the yield point. So as long as your C over D actually is going to be less than 0.6, you should be fine. Your assumption was correct, if this makes sense to you. Here is the reason. When the strain in the steel is equal to 0.002, C over D is equal to 0.6. If your C over D ratio that you just calculated out is going to be less than 0.6, it means your assumption is correct. Because this happens, the 0.6 happened at 0.02. And this is going to be the directional increase of the strain. So we should be fine. Another example here. I have taken the same concrete section. The concrete strength, I made it 5,000. So what is the similarity between this and previous problem? I'm going to say, well, same depth, 16-inch, same width, same clear cover, same tie size. Concrete strength went up. Steel strength or yield is the same. And it says here, use 10 number 8 rebars. Now, instead of having how many rebars in this case? 3 number 8. Now I added 10 number 8. I'd like to see what is the consequence if I added lots of rebars in 3 and just added 10. I mean, would I end up with the phi factor of 0.9? Would the strain in the steel is going to be like over 0.002? And what is the 0.002? If you do not remember, the 0.002 is going to be the yield point. So, okay, let me try this example here. I'm going to do exactly what I have done the previous example. I'm going to start here by looking at the depth. It's going to be the same. AS now is different now because I have 10 bars. 10 rebars is going to be 10 times 0.79. It's going to be a lot. And this is going to be usually like my assumption. I'm going to just assume that the strain in the steel is going to be higher than the yield point. But I don't know if this is going to be true or not. I'm trying here to find out the A, compression block depth. And look what happened. I used to end up with 4 inches. Look how many inches do I have? 11.15. Doesn't make sense. This depth here is just big. This is too much. It's almost close to be the depth of the beam. It doesn't work this way. And look at this number here, the C, the neutral axis depth, 1394. So what happened? Just my analysis doesn't make sense because this C here, the block depth is going to be deeper than just D. You remember D? D is equal to 13.5. Let me go here. You remember the depth, 13.5 inches. Now, my analysis says compression block depth is going to be 1394. Let me take you back here to this picture. So in the new example here, the C, which is this neutral axis depth, turned to be right here, even larger than D. So it doesn't make sense. Something is wrong with my equation. I'm going to say, this cannot happen. And here's the reason. I have an assumption here. I said that the stress in the steel is going to be equal to 60. But this seems to be wrong. Because when you look here at this equation, when you add higher F sub y, this A depth is going to be a lot. It's going to be big. And this cannot be true. I mean, the depth of the neutral axis cannot be equal or more than the depth of the beam itself, like D. So what happened is this 60 is incorrect. It doesn't work like this. So my assumption is wrong, and I need to solve for the stress in the steel. But how can I start in this case? All right. Let me do here the compatibility condition. What is the compatibility, which means the strength? Now, in the past, what I did, I used to put this equation here and put F sub S, which is the stress in the steel, to be equal to F sub Y. And with that, the problem was very simple. It was much easier because I was able to solve for A, take the A, find C, and then after you find C, dC over D, you get the phi factor, and then you're done. Now, in this case, I cannot solve it this way because actually I don't have this Fs. So Fs is going to be one of the unknowns. So in all the previous example that we have done, I used to have one unknown and I was able to solve for it for quick. In here, I have more than one unknown. I don't know A, I don't know Fs. Now I have two unknowns in this problem. One of them is going to be this A, the other one is going to be F sub S. You look here at the rest of the parameters. Do you have AS? Yes. Do you have B? Yes. So my two unknowns is going to be Fs and A. So I said, okay, what should I do after this? I said, okay, let me also, instead of using A, I'd like to use C. How can I do this? Say, okay, I know that A is going to be equal to C times beta 1, which means C is going to be equal to A divided by beta 1. So let me remove this A and put C times beta 1. So, okay, I'm just taking this equation and try to rewrite it again. A is equal to C times beta 1. The yield strength, or the stress in the steel, generally speaking, is going to be equal to ES times epsilon S. So any stress in the steel is going to be equal to ES times epsilon S. Let's take here, this is steel. Stress is going to be equal to ES times epsilon S. So what I have done, I've taken this equation, I changed a little bit Fs and A. I changed this variable, so this limits. So good, all right. Now let me put all the numbers I have in my example here. Beta 1 is going to be equal to 0.85. I understand that. But I can cross it out with, can I cross it out with any other factors? Let's see, no, hold on. Let me put here AS. Let me put here ES, the 29,000. So, okay. Let me take beta 1 and throw it on the other side, which is the 0.8 in this case. Why beta 1 is equal to 0.8? You say, well, let me take you back. When the concrete strength is equal to 5,000, according to this chart, how much is beta 1? Let's say, okay, beta 1 equals
0.85, said.
Yeah. Go ahead.
You said if it reaches 4,000, correct?
Yes, but the concrete strength we're using this example is 5,000. So in the second example, we made the concrete strength as 5,000. So when you have here 5,000 or 5k psi minus 4k psi is going to be 1 times 0.85. It means beta 1 is going to be equal to 0.8. Let me move forward to our example. Here's the strength in the concrete. Concrete strength is 5,000. Okay, fine. Now moving forward here, this beta 1 is going to be equal to 0.8. B is a 10-inch. F prime C, 5k psi. I'm going to go back here and ask you a question. I remember I have said that this code and all the equation has to be in psi, unless you know what you're doing. So is it okay to use F prime C here to be 5 and not 5,000? Question to you guys. And why it is okay?
Because we have the modulus of elasticity in KSI, so it's okay to.
This is correct. Absolutely. This is correct. If I put this modulus of elasticity to be in psi, I should use this in psi. So I got to be careful because I need to balance the units. So in some equations, it's going to be simple if you like to do it this way. But if the equation includes square root of F prime C, you cannot do it. You cannot do this straight. So I'm going to say here, here's the first term, AS, ES, epsilon S, I don't have it. And here's the 0.85, 5k psi, 10, and then this is going to be beta 1 coming from the other side, is going to be 0.8. Now, I was able to establish an equation for relationship between the C and epsilon S. And this is what I'm going to be calling here equation 1. So in equation 1, I'm relating C to the strain and the steam. Now this is going to be my two unknowns. So I started here my unknown with A, which is the same as C, right? Difference is going to be, A is going to be equal to C times beta 1. So instead of A, I made it C. And instead of Fs, I'm using here epsilon S. And I know the relationship between epsilon S and Fs. Relation is going to be ES, the modulus of elasticity. Now I have one equation contains my two unknowns, which is the strain in the steel and the neutral axis depth. I said, okay, great. How about the second equation? You know, if you have two unknowns, you need to have two equations. Here's the second equation. Now, where is this coming from? You're going to say this is going to be coming from the two similar triangles when you're talking about the strain. So I'm going to take you back here to the previous example and see how it is written. You're going to be looking at this. You're going to see here, how about the strain? Let's say that you don't have the strain here and you don't have C. How your equation is going to look like? You say my equation is going to be 0.03 divided by C, correct? For the first triangle. For the second triangle, it's going to be epsilon S divided by D minus C, which is this distance here. If you think about this equation that I'm just talking about, it relates the depth C to the strain in the steel. And this is going to be my second equation. So the first equation is going to be based on equilibrium condition, which means that you put C equals to T. And based on this, you find out the relationship between C and the strain in the steel. In the second equation, based on this similarity, you're going to be able also to find the relationship between the strain in the steel and between the depth of the neutral axis C. Any questions?
So with these equations, for example, the first one, A is equal to AS times FS, the very first one. So is that divided by the entire?
Yes, by the whole
okay.
thing. It is
Okay.
ASFS divided by, and then you have this bracket, the whole thing is going to be inside.
Okay, and same thing goes with C beta 1, right?
Yes.
Okay, thank you.
No problem. So now I have two equations for the two unknowns. Two unknowns again is going to be the epsilon S and the C. Neutral axis depth and the steel strain. I can solve both of this together and find out C and epsilon S. So, okay, good. Here is C. Can you find out A? What is A? Compression block depth. Now, how do you do it? You just take this C multiplied by beta 1. And how much was beta 1? Beta 1 is 0.8. So from 926, you're going to end up with 741. Okay, good. It's very good. Now I have the A compression block depth. That's it. Anything else you need? I'm going to say, yeah. In order for me to solve for the moment, I need to have Fs. Now I'm going to ask you, what is the relationship between the two? I say, okay, here's the relationship. The stress in the steel is going to be equal to ES times the strain. Okay. Here is the strain in the steel, multiplied by 29,000, which is the slope of the line, the elastic range. You're going to give you a stress of 31.9. Therefore, the stress in the steel, in this case, it is not really 60. And we ended up with having stress case and the strain case is going to be within the elastic range. You're at a point here, maybe right in the halfway through it. Makes sense, because the strain in the steel is 0.0021 and the yield strain is going to be 0.022, then you're therefore that you're half the way between the 0 point and the yield point. Also look at the value here, 31.9 makes sense. It's about 30 KSI, and it's going to be like half of 60 KSI. Now, how about the phi factor? I said, well, phi factor, do you want to do it based on the strain in the steel or based on C over D? It's going to be up to you. So let's do it based on C over D or the strain. We're going to do it both. Going to move here to this. You're going to say now the strain in the steel is going to be 0.001. We are going to be in this range here. And also C over D is going to be higher than 0.6. Yeah, it's going to be 0.68. So it's going to be in this range. So what does it mean? It means that I'm going to be using here this solid line. And in this case, phi factor now becomes 0.65. Now here's something new that I learned. Adding lots of reinforcing is going to reduce the phi factor. I was not ready for this. I thought that I'm gonna start here with 3 number 8, I'm gonna be adding 10 number 8, and everything is gonna be good. It turned out that it's not that straight, because what happened, the phi factor has been reduced, which means if you think that, let's say, the moment capacity is gonna be equal to about 120 for the 3 number 8, you remember this 120 kilowatt? I'm gonna take you back to our example. About 120, 122, right? This is gonna be for 3 bars. If you make him 10 bars, you cannot just take this value multiplied by 10 over 3. It's not gonna work this way, because what happens, the phi factor has been dropped a lot from 0.9 to 0.65. So here's what I was thinking about. Let me put it here. I was thinking, if I have here 3 number 8, and they have the moment, so I'm gonna say here's the reinforcing, 3 number 8, and the flexural capacity is equal to 1 to 1 or 1 to 2, roughly. This is gonna be the moment, and this gonna be the reinforcing. So what happened here? If I have here 10 number 8, I was thinking it's gonna be 10 over 3 multiplied by this number here. I'm gonna be getting like 406. It's gonna be like 3 times. But here's what happened. The transduction factor has been reduced. Now let me see what's gonna happen here in my answer. Here is phi min or mn first. As times Fy. Here's As times Fy. D minus A over 2. Here's the flexural capacity, 205.7. Let's say about 206. Multiplied by 65.65 is going to be 133. Look at this analysis here. I thought it's going to be 400. It went up from 122 only to 133. So actually dumping lots of reinforcing in the beam is not a good idea. All what I did, I took it up from the 122. I thought it's going to be 406. Look at this, 133. The increase would not that like 3 times, because I have big drop in the transduction factor, which is a phi factor. Like to hear from you guys. This is going to be a very critical issue. You're going to see it in a homework, and certainly you're going to see it in the exam. So I'd like now to hear from you. You don't want to skip this chance to ask me questions on this.
Sorry, how did you get FS again? I know you used like the graph.
How did I use the 0.65?
How did you calculate FS?
FS, all right, very good question. Any questions before this? Here's FS. But do you guys have any questions before this issue? Like in here. I'd like to see if you guys are okay with this item number 2. Is everybody okay with it? It is your chance to ask me to repeat it if you still didn't get it.
So are you saying Fs and is equal to Fy, but that's why they're interchangeable? Because we have As times Fs, and then we threw in.
This is here, if you like to use this equation, right? Okay. So instead of, if you like to use this equation, let's say you decide to use this equation. Now this is going to be epsilon y, if you like. This is going to be epsilon y. So this equation is valid. At any point you can say Fs is equal to Es, I don't like the font, times Es. This is going to be like the general way of looking at this equation, like the general equation. At one specific point, you can say Fy equals to Es times epsilon s. This is going to be like a special case, but here's the general case. So what I'd like you to use is to use this one. This is exactly what I have used here.
Got it, okay. All
right, so if you like, just to make it simple for everybody, I'm gonna say, you know what? Just cross this out and put y instead. If this is gonna make it simpler for you. Yeah, should be like this, right? This is gonna be simpler. So is everybody's good with item number 2, finding out these 2 equations, or not yet? I'm repeating it again. Are we good with number 2 or not yet?
Yes.
Is that compatibility equation is always going to be the Fs equals to Es multiplied by epsilon s?
You're talking about this equation?
Yes.
Yes.
that's a fix. Okay.
Yes,
So the issue is defining equation number 1.
yes, because this one we had it before.
Okay. Thank
This
you.
one we had it before. It's gonna be exact same one. Let me confirm it to you.
I mean for other problems.
Yeah, this is a standard equation that you can use it. Yes, this is correct. This is about the strain compatibility. Yes.
And we got that from similar triangles.
Yes.
And
So the biggest, oh, sorry.
go ahead.
So we realized that the first time we did the procedure didn't work out because our A was greater than our B. So that was a big warning sign, like, okay, we can't just assume that the.
Yeah, because this here turned to be big. It's just 11.15 inches, and the C neutral axis depth is gonna be 13 inches. 13.9, which means it's almost, it is more than D, the depth D. It doesn't work this way.
Mm-hmm.
So there is no way that the A is gonna be there.
Oh, okay. Yeah. And that's why we had to solve it around this way, the second method, to make sure, because our assumption in the beginning was incorrect, so we have to figure it out on our own.
Yeah, and let's say that you'd like to move forward, right? Let's say that you said, well, I'm gonna go here with this. C is gonna be equal to 13.94, right? What should I do with it? All right, here is A. How about D minus A over 2? Now find out the strain in the steel. How would you find out the strain in the steel? If C is gonna be deeper than D, look at this figure here. If this C is greater than D, what are these two triangles then? You don't have them. You're gonna have one trapezoidal. And this will never happen because you need to have tension side and compression side. This result that I'm getting here for the A or for the C to be more than the depth, it means that the entire section is going to be under compression. Right? So in here, I have section 1, the top of the section, I call it compression. It's going to be tension. This is what I'm expecting when I have moment acting on the section, on the beam section. But when I'm receiving here, C value to be greater than D, it means the entire section is going to be in compression. Does it make sense?
Yeah, it makes sense.
So can we say in general, if C becomes greater than D, then we have to go through compatibility equations. It means that FAS is not equal to FY.
Exactly. So therefore, my assumption, the first assumption that I put here, which is this one, right, is wrong. This assumption is incorrect. And it says here, has not yielded. I mean, the assumption is incorrect.
Thank you.
No problem. I'm very happy with this discussion. So now I guess we understand that we have two equations, and if we solve them, what's going to happen? I have two unknowns. The first one is going to be the strain in the steel. The second one is going to be neutral axis depth. So I'm going to be solving for C and epsilon S. So what do you do after you have the epsilon S? You're going to go here to this equation. You're going to say, here's my equation. Fs equals Es times Es. This is going to be the modulus. This is going to be the strain, like epsilon, if you like. So what I need to do is take the strain here, multiply by 29,000 to solve for F sub S. Now, did they answer the question about how did you find out F sub S? Or not very clear?
Yeah, it's clear.
Right, good. Good.
Professor,
Yes.
is it C over D more than 0.6? We should check. Not just only C more than D. If C over D is more than 0.6, we should check.
If C over D is going to be more than 0.6, it means that you're going to have compression control, and your phi factor is going to be 0.65.
So if another question,
yes,
C is not just over D, it's like over maybe it's 0.8 D. So we still should we should not use the assumption epsilon S over epsilon Y.
This is correct. So here's just to confirm your point here. So we said here we have two cases. At one case, we found out the strain is going to be 0.05 in the first example. In the second example, C is greater than D. We said it doesn't make any sense. How about if it happened in the middle, right? This can be also a question. What happened if C is about here? Let's say that I solved and C was about, let's say, 10 inches. What should I do? It still sounds big, right? So I'm going to say something here might not be correct. But you know what? Let me find out the strain in the steel. So if you take the C that you just calculated to be 10 inch, you try to find out the strain in the steel by doing this line like this, right? It's going to be looking like this, the strain, right? Does it make sense? Are you guys following me? Okay.
Yeah.
So the strain here is going to be 0.03 and the strain at the bottom is going to be so small, right? The strain in the steel is going to be so small. So it's going to be lower than what? Lower than 0.002. Lower than the yield strain. So you're going to say, well, this assumption is wrong. I just tried to confirm it. I tried to confirm the strain in the steel and this assumption turned to be wrong. Therefore, I don't have the strain in the steel and I don't have the stress. I assumed here that F sub y is going to be equal to the stress in the steel and this is not true. So now I need to do it this way, the longer way. All right. More questions?
So can we say that the stress should be actually beyond the yield in order to still to sense that stress?
Say it again, please. I'm sorry.
I mean, if the stress doesn't get to the yield point,
yes,
it is smaller than yield stress.
Yes.
In that case, the steel doesn't feel, doesn't sense the stress.
Yes. And therefore, you need to find it out this way.
Yeah.
You need to have two unknowns. In the first example, I just make it simple, right? Because I say, let me assume the strain in the steel is going to be higher than the yield point, and therefore the stress in the steel is going to be equal to F sub y. And with that, I have just one unknown, which is the C or the A. But if the steel is not yielding, it's going to be a little bit more complex, like in here. This is going to be a very good exercise for you. I want you guys, once you have the time, you try to resolve this problem again. All right, are we good? More questions? Look what happened. I started with 122. I said that this is going to be 3 times the trends than this, and I expect it to be 406. But the analysis says it's going to be only 133. So the increase is going to be very small. I just added lots of rebars for nothing. So it is not that good when you dump lots of reinforcing. You got to be careful for the amount of reinforcement that you put in there. Don't think if I'm going to be adding lots of reinforcing, this is going to be good for my structure member, right? Don't consider it this way. This is going to be the lesson out of this 2 examples. Sorry, I cut you off. Go ahead.
No, I was just telling you, yeah, it makes sense what you were explaining.
So is there a way that we can calculate the right amount of rebar to find the right amount of rebar?
Yeah, we're going to be coming to this. We're going to have more examples and we're going to show what is the best way of getting to the right amount of rebars that you need.
Okay.
Because what do you need this rebar for? I'm going to be asking you this question. I mean, why? How do you come up? What's the importance of having this reman? How do you assume the rebars first? Do you start by putting the rebars in the beam? Or do you start by having the loads and then you figure out the moment demand, M sub U, and then you say, let me solve and find out AS? Which way do you think you would start in a standard case, like in an actual practice? You are the designer now. So I guess you're going to say, well, I'm going to start by having the section, like 16 by 24. This is going to be the size of the beam. Now I cannot put the reinforcing unless I know how much demand I want to put on it. Once I know the demand, I'm going to do something there to start with the first AS, like the first estimate. We're going to be going through this in some examples. Can we move forward to the next slide set? Or we still have questions?
I'm good.
All right. The slide set has been there now online for a while. And we're going to continue this rectangular reinforced concrete section. This is rectangular. It is true that you may have a small flange on the top, but if the entire flange is going to be falling into compression, we're going to consider it to be a rectangular section. Here's another example. Beam size is a little bit different. It's going to be 16 by 30 inches. The distance from the bottom to the center of the rebars is given at 3 inches. So you don't have to spend the time, find out the ties and the rebar size. You're going to say here the depth is going to be 27 inches, 30 minus 3 inches. All right. And then the rebars, it says that you have 2 number 8 plus 1 number 9. I said, well, how would you do this? I said, I can have here 1 number 8, 1 number 8, and 1 number 9 in the middle. I should be able to do it. I don't really have to have the same size of rebar when I'm putting them all together. I can work with that. So 2 number 8 rebar, if you guys recall, is going to be 0.79 square inches, and number 9 is going to be 1 square inch. I should be able to find out this AS easily. It says here concrete strength is going to be 3,000, and yield strength is going to be 60,000 psi. I said, okay. So what are you looking for? Of course, it's going to be Feynman, right? It says here determine the following. This is going to be in the second slide. The mud structure. I'd like her to have complete analysis of this beam section. What's the mud structure? Anyone recall this F sub R or sub CR? Anyone recall the equation for it?
That 75, 0.75 FSC.
7.5, yes. Square root of
7.5, yes, cool, yeah.
F prime C. This is correct. And this is here the cracking moment. Definition of the cracking moment is going to be that moment at which the bottom of the beam, because this beam here is exposed to positive moment, the bottom of the beam tensile stresses is going to be reaching the rupture stress. It says effective depth. Effective depth has much to do with this cracking moment and F sub R. Effective depth, this is when you use the reinforcing, you try to find out here the last item in our analysis here, which is Feynman. Compression block depth, A. Yeah, I remember the equation. The C, I need beta 1. The strain in the steel, okay, of course. And for that, I need to confirm that the strain in the steel is going to be more than the yield point. Nominal moment strength, MN, and then you do the phi factor, and then finally do Feynman. You see here in this example, I itemize all the requirement items here or elements. And the reason is because you need to be used to this. You have certain steps that you need to go through. It is easier for me to grade it. So for example, if I'm going to give here a point for each one of them, I can say this is going to be, let's say 1 point, the depth is going to be 1. This one, I'm going to say maybe, this one I'm going to give maybe 2 points. For the strain in the steel, it's going to be 1, 1, so maybe total of 10 points. So be sure when you're doing a beam section analysis or to find out Feynman that you show each step. So grading is going to be easier for us. Otherwise, I may assume that maybe you did not provide this or it is not clear to me, and then you may lose points. So be sure that you itemize your solution, or you box it in the analysis, or you be sure that you put a line number for it, just to make it easy for us and for you. Okay, here is the cracking stress. F sub CR 7.5 square root of 3,000. I cannot say here square root of 3 and then divide the whole thing by 1,000. And for that, the tensile stress or the cracking stress is going to be equal to 410 psi. All right. How about the cracking moment? How can I find out here the cracking moment? Now, in this case, this section, the entire section here is going to be exposed to homogeneous stress because the beam is not cracking yet. and the rebars has been ignored in my analysis because I'm still within the cracking point. So I'm going to say the stress is going to be equal to the amount divided by the section modulus, not considering any of the rebars. Section modulus is going to be PT squared divided by 6. This T is going to be the same as H. It's going to be 30 squared. And the B, the width, is going to be 16 inch. You divide this by 6. You got this number here, 2400 inch cube. This is going to be the section modulus. Okay, here's the moment. This moment is going to be equal to S multiplied by F sub CR. And with that, I'm getting here 98,400 pound-inch. I'd like usually to see the moment, and please keep this in mind. I'd like to see usually the moment in my analysis. I'd like to see it as in kip foot. So how would you convert from pound-inch to kip foot? Can someone help me here? What is the conversion factor in this case?
For the feet, multiplied by 12, or yeah,
Should I
multiplied by
multiply or
12.
divide?
Oh, divide.
I have lots of pounds, inches.
Mm-hmm. And
So
then
from
for
inch to a foot,
mm-hmm.
divide.
And then for the pounds, divide by 1,000.
Very good. Thank you. All right, item number 3, the depth. Saying, well, this is easy because what you need to do is just take 30 minus 3 inches because the 3 inches was from the bottom fibers of the concrete section to the center of the rebars. That was 3 inches, 27 inches. Any questions? Huzaifa?
Yeah, I'm good. I'm good.
Good? All right. AS, I have 2 number 8 and 1 number 9. What's the cross-section area for them? All right, I have 2 times number 8. Each one of them is going to be 0.79 square inches. And for number 9 is going to be 1 inch, total of 2.58. Same assumption that I'd like to start with, just to make my life easier. If it didn't work out, I need to do the 2 equations and 2 unknowns. Now I'm going to sit here, tension is going to be equal to compression. I'm going to be using this my equation. AS times Fy, as in 6K psi, now is going to be 154.8. 0.85 times F prime C, compression block stress. Then times B, the width of the beam, the 16 inch. So I have 3.8. This number sounds good. I mean, I don't think that we're going to be in trouble when it comes to the strain in the steel, but I have to finish my analysis and complete my work. Now, the C, which is neutral axis depth, is going to be equal to A divided by beta 1. When I have here 3,000, my beta 1 is also 0.85. So usually, if the concrete stress or strength is 4,000 or less, my beta 1 factor is going to be 0.85. So yeah, I said fine. Okay, here's the 4.5 inches. Now, in this case, right, like in this analysis here, again, what I have done, I set the tension to be the same as the compression in my equation, which is right here. And based on this, I was able to solve for A, compression block depth, and the C, neutral axis depth. Great. How about now the strain? Yield strain. How much is the yield strain? Yeah, take F sub Y divided by 29. I know this value before. I have used it. I've seen it. But I need to show it here. How about the strain in the steel? Actual strain in the steel. I said, well, this give me the same equation I have used in 2 previous examples. Now you guys know where this is coming from. Anyone can tell me what was the principle or what is this based on, this equation? Based on what?
Similar triangles.
Yeah, similar triangles for the strain. So I'm going to put here the D, the C, the strain in the concrete, the C again. With that, I have 0.015 strain in the steel. This is good. Now I have no problem for the strain in the steel. My assumption was correct. Therefore, the stress in the steel is going to be equal to F sub Y. This is great. How about M sub N? You can see, yeah, it's going to be equal either tension or compression. So this one here, I have used the tension, AS times Fy, the 154. D minus over 2, it's going to be 27. And don't forget the C, it is not really the C that I'm going to divide here by 2, it's going to be the A. So I'm going to go back. Your A value is 3.8. Divided by 2 is going to be 1.9. Now I have MN as a kip inch. To convert from kip inch to kip foot, Should I multiply or divide by 12?
Divide by 12.
Divide by 12?
Divide.
Yeah, because if you have inches, means that you have too many, you'd like to reduce it to a foot, you divide, you don't multiply. Now look also at the strain. The strain in the state is going to be 0.015. Is this good for the phi factor? I'm going to say, you know what? Let me go back and check the chart. 0.015. Not in this one. Should be in the other one. .015. Wow, this is going to be here, right? You have lots of strain. This is good. Your phi factor here is 0.9. Okay, so what should I do next? 0.9, take the 0.9 multiplied by m sub n. Now you are going to have the phi mn, which is the strength of my section. I'd like here to have some conclusions based on this example and the previous examples. We started by assuming or giving you some reinforcing bars, amount of reinforcing bars. In one case with this, we said 3 number 8. Another case we said 2 number 8, or maybe 2 number 8 and 1 number 9. Also, the size of the concrete section was given, and the material properties was given to you. What is a material property? Like what? Like, for example, I said concrete strength is going to be 4,000 psi, or 5,000, or 3,000. So I give this to you. Also, I told you the steel is going to be grade 60, which means yield is going to be at 60 psi. How about in practice? Who's going to give you what? Well, in actual practice, I need to come up with the trends I would like to use in the project. So this is going to be my responsibility to come up with this trend. Now, what trend should I go with? Should I go with 3,000, 4,000, 5,000? Right? Because these are the numbers that you have seen. Now, once you start to practice, you need to come up with this value. Usually, you're going to have a senior, like project engineer that you're working with him in this project. He's going to tell you exactly which value to use. Just so you know, if you use 2,500 psi, which is the lowest number in the ACI, you don't really need to have official inspection. Are you guys following me?
Yeah.
Okay. So if you're doing a project and you'd like to save some money, you don't want to spend money on the inspection, which means that you don't really need to have deputy inspector or an inspector who's going to be going to the site, take concrete samples and test them. You use a strength of 2,500. So you got to be careful. Are you doing a very small job, like a small residential project, and you have wooden structure, like light framed wooden structure above it? Or are you talking about 2-3 story building? If you are talking 2-3 story building, it's going to be worth here the time and the money that you spend on inspection. But if you are just doing some foundation, let's say for some slab and grade or a driveway, so don't go 4,000 or 3,000, you go 2,500. If you are doing little foundation for a small house, so of course use 2,500. If you are doing an elevated slab, let's say in one of the school buildings, you should not go below 4,000. So usually it's going to be 4,000 to 5,000. Now you have an idea about the trends and where we come up with the strength that we assume here and the reason. Now, other question here. Let's say I assume I'm going to be going here with 4,000. What type of cement? You guys recall type of cements? The common.
Isn't it Portland?
Type
Yeah.
2.
What type? Type what?
2.
2 and
2.
5.
Type
and
5.
5. Where would you use 5 and where would you use 2?
2 is general. 5 is ocean area.
Or sulfate exposure, the foundation. It happens a lot. That you look at the soils engineer or soils report or geotechnical report, and then he says that the soil is very corrosive. It has lots of chlorides, In this case, you'd like to use here type 5. So you'd like to protect the foundation. So in this case, use stronger cement. So now you have an idea about the material properties, like in the concrete. What strength, what cement type. This is what you're going to be specifying here in your design. Now, how about the grade of the steel? Just, you know, we have two common grades in the market. We have grade 60 and 75. 60 is the common one that you find everywhere. Don't try to go to 75 unless you have lots of rebars in your design and you feel it's going to be just the beam is going to be congested. It is going to be very tough to pour concrete. So in this case, you put grade 75, right? Does it make sense? So you know where to come up with the properties of the steel and concrete. Now let me continue. In your beam here, I give you the beam depth and width, and also I give you the reinforcing. In reality, you don't really have this. What you have is going to be the loads. You know the span of the beam, you know the dead load, you can figure it out, and then you know the life load. So you're going to be doing here dead load on life load and answers. And with that, you're going to have the demand. Once you have the demand, what do you do next? You say, well, let me throw there some steel that I don't know yet how to come up with the first estimate for the reinforcing bars, and then try and find out Feynman, and then you go through this exercise that we went through. So in this exercise, what I have done, if you recall, I ignored the top reinforcement. I didn't give you any beam with some top reinforcing here, right? It is usually just the tension reinforcing, which we call the compression or the hangers reinforcement. And I consider the beam design here to be a rectangular section. In reality, most likely, I'm going to say here, in 95% of the cases, you're going to have here a T section that I'm just ignoring the T for now. So later on, you're going to see here a T section, and then you'll learn that you can ignore the T in some cases, and in some other cases, you do not ignore it. And in this case, what you need to do is to consider the T effect, and then you start to use it because it's going to help you out in your flexural strengths. Also, the compression reinforcement here is just ignored. But later on, you will learn that the compression reinforcement here is going to help you out to increase the strength, the Feynman, a little bit. Which means if I take this beam here, and you have a couple of rebars on the top, and they put them in the analysis that you haven't seen yet, because all what now you have learned is how to find out Feynman for rectangular section with only tension reinforcement. We're not talking here about doubly reinforcing beam, which means compression and tension. And in this case, the compression reinforcing is going to be adding a little bit to this flexural capacity. I'm going to say maybe 10%. So it's not going to be much. So if your design is kind of tight and you'd like to reduce the rebars on the bottom, so what you can do here is to add a little bit of the compression reinforcement effect, because the top reinforcing, you need to have it anyways. You cannot have a beam without the compression reinforcement. Let me go there. Look at the beam. You need to have some rebars here on the top. You cannot build the beam without having top rebars. Otherwise, what are you going to be hooking these ties to? It's going to be loose on the top once you put concrete. I mean, it's not going to be doing any work here for it, but you need the ties. We're going to be talking about the use of ties later on. Any questions before we go? If you have no questions, go ahead and sign out. Type your name, please, and leave. If you have any questions, stay here with us.
I had a question.
Yes.
In your assumption, how did you confirm that was a correct assumption?
Which one? This example or the previous one?
For this example.
This one?
Mm-hmm.
Yeah. The assumption of the strain in the steel to be above the yield point?
Yes.
Well, it's right here. I found out the strain in the steel. It is 0.015. And the yield strain is going to be 0.0021. Now, which one is larger?
Yes.
My assumption is correct.
Okay. And
yes.
to find the nominal moments strength.
This one?
Number 7? Yeah. And is this equation from also using similar triangles?
This one?
Uh-huh.
No, this one here, the moment, I'm gonna go back here. You know, the moment is gonna be like the internal moment within the beam is gonna be equal tension compression multiplied by the distance from here to there, right? Which is the Z value. You remember distance from C to T? We used to call it Z.
Oh, uh-huh.
So the moment equals to C or T multiplied by this Z. And this
Okay.
Z is equal to D minus this guy here. It's gonna be the entire depth, D minus A over 2. Now let me show it to you.
Okay.
AS times Fy, which means tension or compression. Now in this case, I use a tension. D minus A over 2, which is a Z,
Mm-hmm.
or Y sub CT, if you want.
Okay. I see. Okay, I see it.
Okay.
Professor, I had a question. Is there homework assigned for this week?
Yes, it will be, you'll have it this evening.
Okay, okay.
Yeah, no problem. Thank you.
Thank you. Have a good one.
You too. Alan, do we have Alan Bond? Did he show up? Dylan Mitchell? No? Daniel? I've seen Daniel.
Professor, I have a question.
Yes?
So for this example, our steel strain is 0.015. Is there any chance that the steel strain too large and coming to the strain hardening region?
Usually this is not a problem, but just, you know, this is gonna happen because look at the equation. What happened to the equation? What's gonna increase the strain in the steam? Strain is gonna be very high if C is gonna be very small.
Yes.
Because what's gonna happen, this line is gonna be doing this, right?
Yeah.
Right? So C is gonna be small. Which means you put a little bit of reinforcing and they're not doing any good. Later on, you will learn that you have a minimum amount of reinforcing that you need to add to your beam. And minimum reinforcement to control the amount of strain and stresses in your steel rebar.
Got it. So we
have,
can.
yeah,
problem.
we call it AS minimum. Yes.
Okay, got it. Thank you.
No problem.
Thank you, Professor.
Thank you. All right, you guys, you have a good night.